Good day and welcome everybody to our presentation on fiber Bragg grating sensor design. My name is Brian Tipper. I'm the VP of Sales and Marketing here at OptiWave, and I'll be sitting alongside your host, Steve Dodds. Before we begin, let me discuss the format of today's webinar. During the presentation, we will have two question and answer periods. The first one at the halfway point and the second one at the end of the presentation. We're not going to be handling questions via the raised hand option, so we ask that you all please type questions into the questions section only. We'll also launch 3 polls, such as the one that you're viewing now. We ask that you please take a moment of your time to answer each one. And finally, we'll be recording the webinar and distributing it to all registrants via download link that you'll receive in an email approximately 2 hours from now. So without further ado, I'd like to hand it over to our OptiGrating product manager, Steve Dodds.
Hello and welcome everyone. I'm Steve Dodds and I would like to show a demonstration of modeling and design of fiber Bragg grating sensors using one of our softwares, OptiGrating. The example that I'd like to show to you is taken from the literature. This comes from the Journal of Sensors and Actuators B. And it's an example of a fiber Bragg grating that can sense salt content of water. If this fiber is immersed in fresh water, it will have a certain optical reflectivity spectrum, but the fiber has been coated with a special material, and this material, if it is immersed in salt water, it shrinks a little bit, and the shrinking applies a compressive strain to the optical fiber and changes its optical properties, which therefore, by making optical measurements, you can determine the salinity of the water that the fiber is immersed in. So I would like to show you the details of how you might characterize and design such a fiber with software such as ours. This is what OptiGrating looks like when you first open it. It's just an empty place. And what we will do is put in this into our OptiGrating project everything that's known about this fiber so far to get started on modeling it. The paper tells us that the fiber is Corning SMF28. So the first thing that we need to do is put in some details about the fiber. And we need to begin a new project in OptiGrating. OptiGrating presents all of the possibilities for grating calculations. OptiGrating can model a Bragg grating on a single fiber, which is what we have today. It can also investigate grating assisted coupling between optical fibers. It can also analyze gratings that are on slab waveguides or slab waveguide couplers, and it can do more general kinds of waveguides as well. But today we have a optical grating on an optical fiber, so that's what kind of project we will start. And now there is a place to enter details about our fiber on which the grating has been written. Nobody except Corning, I think, is too sure exactly what the refractive index of the core of SMF 28 fiber is. But we at OptiWave believe from our own modeling efforts that at a wavelength of optical wavelength of 1.55, which is where our measurements appear to be taken, at that wavelength, we believe that the refractive index of the core of SMF 28 fiber is 1.44926. And we believe that the diameter we believe that the radius of that core is 4.15 microns. And we believe that the cladding of SMF28 is made from pure silica, and at a wavelength of 1.55, the refractive index of pure silica is 1.444. So we believe that this is the refractive index profile, the radial refractive index profile of the fiber that we're looking at. And in the transverse plane, it looks like that. So now that we have entered data about the fiber, we have something worth keeping. I would like to save our project. It's Friday, so I'll call it TGIF. So here is project TGIF. And we have entered data about our fiber. Now that we know, or we believe we know, what the properties of the fiber are, we can solve for modes. And at the wavelength of 1.55, it has found an LP01 mode, and the number to the right of that is the modal index that it has just calculated. We can look for higher order modes too. We could set the azimuth index to range from 0 to something more, and the radial index is going from 0 up to 10. We calculate again and we find only one mode. Of course, if we looked at a shorter wavelength, like 0.8 microns, same fiber, we would find higher order modes. Higher order LP modes are evident at shorter wavelengths. But our measurements are all nearby 1.55, and therefore we have one mode, and its modal index is 1.4463, so on. And this is useful information, the modal index, because looking about what's known about our grating, the paper says that the grating length is 10 millimeters, and it shows measurement results of the transmission spectrum for when the fiber was immersed in various levels of salinity. So for fresh water, if it's immersed in fresh water, the Bragg wavelength, that is the point of maximum transmission rejection, occurs at 1.55632 microns. And knowing the Bragg wavelength and knowing the modal index, we are able to determine what the period of the grating must have been, because the Bragg wavelength and the grating period are connected through the modal index by this simple formula. So the calculation of the mode is useful because it enables us to determine more about the properties of our grating. So now that we know a little bit more about the grating, we can go put in what we know about our grating so far. We are told that its length is 10 millimeters or 10,000 microns. And when I put the Bragg wavelength and the calculated modal index into my calculator, I got a period, and the period that I calculated was 0.5380 That's what I calculated from that. And that's about all we know about our grading so far, but we will come back to this page because we will learn more. We have measurement results of the transmission spectrum. This is a measurement of the spectrum going from a wavelength of 1.556 up to a wavelength of 1.5566. So we're going to calculate what the spectrum would be from the grading that we've constructed so far in the model. And we do, and we get a spectrum. OptiGrating calculates both the reflection. The reflection from the grating is in blue, and the transmission is in red. Only the transmission was measured, so I'm going to put the reflection away. And this is what our model is predicting so far. There is a little tool to extract data from this. And we can see that the peak, the position of the peak, which is the dip in this case, has been calculated to be 1.55632. And then looking at our measurement result, let's make a slightly more bigger picture of the transmission result. 1.55632, that's about here. So that does appear to be the maximum rejection in the stop band, which does correspond to the Bragg wavelength with the maximum rejection when the fiber was immersed in fresh water. So it looks like we got the period right. However, there are some differences. One difference that's somewhat obvious is that in our model, there is a kind of ripple occurring in the pass band, and this is not observed in the measurement. Another thing about our model is that the width of this band is also quite narrow, and also our rejection level isn't quite right either. I'm getting a maximum rejection here of 7.7 dB, whereas the measurement was closer to 9 dB. So this means we need more detail about our grading. This is a picture of the grading so far. Along the bottom, we have its length, 0 to 10,000 microns, 0 to 10 millimeters. And the meaning of this graph is it's trying to show you the index change that is due to the application of the grating. So what I've done here is just made up a grating, which at the beginning, it is causing the refractive index to become larger than the original grating by a factor of 10 to the minus 4, and then becoming smaller by a factor of 10, by the amount 10 to the minus 4, and maintaining that periodic variation throughout the length of the grating. You can't see the variations because the period is so tiny, but this gives you the general shape of the picture. My rejection is only about 7 dB, so that probably means that the actual amplitude of the refractive index modulation is greater than what I specified right now. So I can go back and change it. Instead of having an index modulation of that level, I'll increase it a little bit. And having done so, I do get a greater rejection. And now I'm getting nearly 9 dBs of rejection, which is approximately what was measured. But these other features remain. There's still a ripple in the passband, and it's rather narrow. That is, if we, for example, let's look at the width of the passband at a level of minus 6 dB. When I calculate that, my calculation is getting about 0.9 nanometers in width, but the measured results at minus 6 dB are much larger than that. I'm at minus 6 dB. This width is something more like 0.13 nanometers. It's much larger than the calculated result. Well, these features, the width of the passband and width of the stopband and ripple in the passband, they are well known to be related to properties of the grating. One property that it's known to be related to is the so-called apodization. This is the grating over the length of the fiber, overall 10 millimeters. It turns on suddenly, it maintains the same intensity throughout its length. Most gratings aren't like this. Most gratings will start with a small modulation, become a stronger modulation in the middle, and then become smaller again at the end. This is so-called apodization. And I can do that with OptiGrating quite easily. I just go back to the grating definition, and instead of uniform apodization, which is what I started with, I can select a Gaussian shape. So this will start with something small, become big, and then small again at the other end. When I do that and repeat the calculation, you'll see what happens. Two things happen. First of all, the ripple in the passband disappears, and the rejection, the transmission rejection band got to be a little bit wider too. Why did that happen? Well, go have a look at what the profile looks like now. Now it's quite a weak index modulation at the beginning of the grating. It's getting stronger and stronger till we get to the middle, and then it tapers off again. And that the period hasn't changed. It's exactly the same. But it certainly does change other aspects of the spectrum. We go have a look at some of the details. Like I said, the period has not changed. The Bragg, the maximum rejection is still at 1.55632. 55632, that's where our freshwater measurement was. So the Bragg wavelength has not changed, but it has gotten wider. Oh, there is another issue though. I find that my rejection here is only 3 dB, whereas the measurement was -9. And that's probably because in the course of apodizing this grating, I made it weaker. Overall, its reflectivity is less. So in order to compensate for that, I'm going to have to go back to the grating definition. This number now means the maximum modulation. So it appears that in order to get 9 dB in the maximum rejection, we're going to need a stronger maximum modulation. And by playing around with some numbers for a while, I found that this one seemed to produce the right result. Now I'm getting something more like 9. Let's have a closer look. Yes, indeed, it's about 8.9 decibels, which is quite similar to the measurement result. And now the bandwidth at -6 dB is now about 0.12, 0.13, and that is about the width of these measured curves. So now I'm beginning to feel that by doing this modeling and characterization, going back and forth, changing things, observing the results, comparing them to the experiment of the measurement of the transmission spectrum in fresh water, I'm beginning to feel like I know what this grating is and what happens to it when the fiber was immersed in fresh water. When the fiber is immersed in salty water, some things are going to happen. As I mentioned, this coating of the fiber is going to shrink. It's going to apply an axial strain, and a bunch of things will happen. So before delving into the effect of strain and the photoelastic effect and all of that, I'd like to take a brief moment to have a look at some of the questions you've asked so far. And Brian has some questions for you as well.
Okay, thanks, Steve. I'm going to go ahead and launch the second poll for everybody. If you could take a couple of seconds to answer that, that'd be appreciated. And while Steve's reading through the questions, please go ahead and write any questions you'd like to ask into the questions section. He's going to read through them and answer as many as he can during this session. Anything that we can't answer, we will definitely answer afterwards via email. So go ahead and get your questions down right now. We'll have one more Q&A period at the end of the webinar. So yeah, I'm going to go ahead and close this poll right now and pass the mic back to Steve.
Hello and welcome back. I had one question about the situation from Damien, and I have a feeling that Damien asked this question when I was in the middle of my characterization. So I think we're past that, Damien. Let me know if I'm wrong. I have a question about how to increase the bandwidth of the stop band to about 20 nanometers. Well, if you have a copy of OptiGrating, you'll be able to determine that by your own quick experiments, but you'll quickly find that doing things like increasing the modulation intensity will definitely have this effect, and that grating apodization also increases bandwidth. And another thing that really increases it quite a lot is adding chirp. I'm not going to go into that in today's presentation, but you don't need the period to be a fixed number. It can vary over the length of the grating. And if it does that, you get all kinds of other effects, including increasing bandwidth. And all of those are very quick to investigate by just playing with OptiGrating. I have someone who has questions who seems to be involved with the development of temperature sensors and wants to know, is the FVG fabrication always based on real data of an experiment? Well, I would say that it's there will always be going back and forth. I'm sure that this is the situation in any laboratory. You dial things up, you think you know what you've got, you make measurements, you compare that to simulations. Does that confirm what you thought it was? If your simulations and your measurements are all matching up, then you have some confidence that you know what's going on the table. So I see OptiGrating as being an essential part of this process, not the whole process, but an essential tool in getting the job done. All right, as promised, I said that I would have some words about what happens when this fiber is immersed in salt water and the coating shrinks and we start to get strain. Yes, a number of things will happen. There will be compressive strain along the axis, which in our coordinate system is called x3. That strain will change the spectrum right away because, as already observed, the spectrum is influenced by the period of the grating, and straining the fiber will change the period directly, which has an immediate influence on the spectrum. There's another effect that occurs with strain, and this is the so-called photoelastic effect. If you apply strain, which is here represented by U, there's the photoelastic tensor, and that directly causes the refractive index of the material to change. And as demonstrated earlier, the modal index is quite important, and the modal index is determined by the material properties of the glass of the core, the glass of the cladding. So change those material index, the LP01 mode is going to change that mode, and the grating spectrum will change too. So a couple of words about strain, since this is one end of the photo-optic effect. Strain, you can imagine it this way. Imagine atoms in the glass which have coordinates x before you apply the strain. After you apply the strain, the coordinates will be something else, call them c, and the I is 1, 2, and 3, since we have three space dimensions. Delta x is, imagine two atoms that are close by each other, and delta x will be the vector pointing from one atom to the next. Apply a strain, and the distance between those atoms will become different, delta c. But the rate of the strain with your position is a constant. That's why the strain is a constant number. It's unitless, as you can see, because you're taking meters and dividing by meters. There are three components to this, both strain vectors, to both position vectors. And that's why when you take the rate of change of one with the other, you're going to get a tensor that's going to have, in general, 9 components. But the strain tensor is defined as being the symmetric part of the covariance, and being symmetric, instead of having 9 independent components, it's only got 6. And since it's only got 6 independent components, you can represent the strain as a vector. instead of as a tensor. And you will see in a minute why representing it as a vector is convenient. The other end of the photoelastic effect is the optical part. And the photoelastic effect, it affects the permittivity tensor. And the permittivity tensor is the means by which, if you know the applied optical electric field, multiply that by the permittivity tensor, and that will give you the resulting electric displacement. And the permittivity tensor, for a number of good physical reasons, always turns out to be symmetric as well. So it doesn't have 9 independent components, it has only 6, and because of that, you can represent the permittivity, that is the optical end of this, as a vector of length 6 as well. So having the vectors of length 6 is convenient because we want to identify a relationship between strain and permittivity, and the general linear relationship between two vectors of which are of length 6 is, of course, a 6 by 6 tensor. And here is the photoelastic tensor. So represented in matrix form, what's happening is you take the strain vector, you multiply it by the strain matrix, and you get 6 numbers which are all pertaining to what's happening to the permittivity. So in general, a 6 by 6 matrix would have 36 independent components, but for an isotropic material, it's much simpler than that. For an isotropic material, the photoelastic matrix has mostly zeros of components. And of the remaining non-zero components, there's only really 2 independent ones. So if you know X, that is to say P11, and if you know Y, that is to say P12, you know what all the other components of the photoelastic tensor are as well. So this would enable you to take a known strain, transfect it into this matrix, isotropic material, like glass, like the glass that you have in optical fibers, it's isotropic. Take a known strain, transfect that into the photoelastic matrix, and that will enable you to determine what has happened to the permittivity, what's happened to the optical properties of the fiber. So what about our strain? The strain in our case is quite specific. It is a shrinking coating which is applying a compressive strain along the X3 axis. Most materials, glass included, if you strain them in one direction, if you apply compressive strain in one direction, in the opposite direction, there will be tensile strain. So if you shrink it along axis X3, it will tend to bulge on axis X2 and X1 on the transverse axes. So that's why if we apply a tensile strain or a compressive strain along the X3 axis, we'll get the opposite. If this is compressive, this will be tensile, which is the meaning of the minus sign. The strain is going to be going in the opposite direction, in the transverse direction. And the strain in the transverse direction is less. It's less by the Poisson ratio, which for glass apparently is about 0.17. So apply 1 unit of compressive strain on this axis, so you get a unit of 0.17 compressive or tensile strain in the opposite direction. So that's what this is saying right here, that we have applied a strain of epsilon along x3. So that's why we get that component in the strain tensor at the 3, 3 location. And in the two transverse locations, we're getting these smaller strains in the opposite direction. We are not applying any shear strain, and that's why the off-diagonal components of the strain tensor are 0. So that's why the strain tensor for this example is of this form. If the strain tensor looks like that, the strain vector will look like that. And what happens when we take that strain vector and multiply that into our particular strain matrix? Well, we're going to get something that looks like this. And you can see that nothing's going to happen to the off-diagonal components of the permittivity tensor, the vector components 4, 5, and 6. Nothing happens to them because we didn't apply any shear strain. So the kind of strain that we are applying is only going to change the permittivities in the principal axes. The 1 and 2 are the transverse components, and the 3 is the fiber axis. Another thing that's noticeable here is that if you multiply that vector in on the first line, you get a modification to epsilon 1. Multiply the same vector by the second row, you get the same number because these two entries are the same. So you get the same effect occurs in permittivity in the two transverse components. Something different happens in the longitudinal component, it's true, but there's no change in the transverse components. The same thing happens in two of those, so it's not going to make any polarizing effects on our fiber. And this is just written out what the first and second lines of the photoelastic effect end up being. It turns out that we don't need to pay any attention to the third line, to the modification of the permittivity in the axial direction. And the reason for that is that optical fibers are weakly guiding. Therefore, there's going to be a negligible component of electric field in the longitudinal direction, in the x3 direction anyway. So the only significant optical effects is what's happening to the material of the transverse components of the permittivity. That is to say, components 1 and 2. And both components 1 and 2 are summarized by the same equation. So now that we know what's happening, the next step is simply to put these predicted effects into our OptiGrating model. And there is a place to do that. I'll show you where to find it. There's a fiber Bragg grating sensor dialog box. And if you go here and go back to our grating definition and click on sensors, there it is. It's the fiber Bragg grating sensor dialog box. And all of the parameters, physical photoelastic parameters, photoelastic coefficients are listed here. These values of P11 and P12 have been proven to be good for optical glass, such as you find in optical fibers. And anyway, whatever numbers you put in there, they will find their way to the appropriate place in the equation as shown here, and the Poisson ratio of 0.17, it appears in the equation in that place. So this is how everything goes in. Right now, the strain is 0. So what I want to do right now is experiment with applying a little bit of compressive strain. This is what could be expected to happen if we put the fiber in salt water. We expect that coating is going to shrink. That will make a compressive strain, which means it's going to be negative. And I've taken a wild guess as let's apply 50 picometers per micron of strain. So that is, if the fiber was a micron long, now it's going to be 50 picometers shorter. And if it's 10 microns long, it's 500 picometers, and so on. So let's apply that strain. Let's see what happens. And let's go to back to our let's go to our measurement results to see what's happening. This is what was measured from the paper. So right now, before applying that strain, our peak is at 1.55632, 55632. Yeah, that looks like the measured spectrum for fresh water, which was the first target, the reference point. But now I have applied a strain of 50, a compressive strain of 50 picometers per micron. And let's see what happens when we calculate the transmission spectrum again. And oh yes, I do see a small blue shift. Let's see just how big it was. Now, I'm still getting the same sort of shape, a bandwidth of 0.12 nanometers at the level of -6 dB, but the peak has shifted. Now it's 1.55625 or 626. So 1.55626. That might be about 626. Yeah, that might be about there. And that looks to me to be the strain that was measured when the fiber was immersed in water with a salinity of about 0.3 or 0.4 moles of salt per liter. So that's an example of the modeling of fiber Bragg grating sensors, using OptiGrating as a tool to help you out with the modeling and characterization of gratings. And I hope that you enjoyed my presentation. I would like to stop now to ask to have a chance to read more of your questions and to give Brian another chance to ask you a few more questions himself.
Okay, thanks, Steve. So we have one last poll that we'd like everybody to take a second to answer. And while you guys are looking at that, and while Steve's reading through the remaining questions, as I just wrote, if you have any questions that you'd like to keep private, of course, you can just email these to support@optiwave.com and we'll answer them privately so that you don't have to provide any confidential information over the webinar session here. Also, the video of the recording for this session is going to be emailed to the email address that you used to register exactly 1 hour after the session ends. So anybody that registered, any of your colleagues or friends that might have registered but they weren't able to attend, they'll also get this in an hour after the session's over, so you can let them know that. Yeah, so if you have any questions, this is the last chance to ask while we have Steve on the line. Otherwise, you'll have to email us. So with that, I'm going to go ahead and close the poll and hand the mic again back over to Steve.
Welcome back. There is a chance to answer a few more questions before I say goodbye. I've been asked, is it possible to design a grating that can both compensate dispersion and act as a sensor at the same time? Well, maybe it's possible, maybe it's not, but I know one thing for sure. If I was going to try to answer that question or investigate something like that, my first stop would be OptiGrating, because it would permit me to try out all kinds of experiments of different kinds of gratings very quickly, and that would be my go-to. That would be my advice. If you want to do something like that, try playing with OptiGrating first. It will tell you a lot, and if that can be done, chances are you're going to be able to find it using OptiGrating. I have another question. Is OptiGrating able to create two gratings in same fiber? For example, one at 1548 and one at 1550 nanometers, separated by 5 millimeters. And the answer is yes, OptiGrating can do that. In today's presentation, I showed you one grating. And I did some things like apodize it and modify its strength and so on. But I could put two gratings and make them different. And I can also put an empty space, which is here called phase shift, between the two of them. So what you're talking about, to have two gratings, one after the other, going on the same fiber, yes, you can model that in OptiGrating. And if I do that, I'm sure it's going to make a terrible mess of my spectrum. Let's see what. Oh yeah, terrible mess. So yeah, you'd have to take control of that. I have another question. Can we model a fiber Bragg grating in a polarization maintaining fiber? And I would say, well, that's pretty well what's going on by default. If you have a fiber that's got that can wander its polarization, that's going to be an issue that OptiGrating just isn't going to touch. So it's kind of it's really neither here nor there, the polarization maintaining part for you. That's going to be influencing your consideration of your experimental setup and so on. It's not really going to enter into simulations with OptiGrating. Another question about modeling second and third order gratings. Yes, OptiGrating can do that. Of course, I was looking at first order gratings. Here the order is 1, but if you want to look at another order, you can do so. If I do that, I suppose that's probably only one of the gratings right now. I guess I'm going to have to go to shorter wavelengths to see anything, since the other shorter wavelengths to see anything at all. Yeah, I'm not picking up anything on 0.16, so I guess it's got to be shorter than that, doesn't it? I gotta go to something shorter again. Enter a number. Okay. No, I'm not seeing it, but never mind. Don't worry, it can do second order gratings if that is what you desire. I'm asked if the index modulation depths that I've been using are realistic. I think they are, because I have just finished matching my model to real experimental results. If my modulation depth was unrealistic, I wouldn't have been able to do that. I have a question: is it possible to simulate tilted fiber Bragg gratings with OptiGrating? Yes, you can, although in my experience, tilt usually appears only in the context of long period gratings, when you're looking at the issue of coupling to cladding modes. But the short answer to your question is yes, OptiGrating can do that, and yes, there are examples of that in the samples that come with the product. Yeah, more questions about my model being realistic, but I'd simply have to point in the same direction. I matched the simulation results to the measured results. That's about as good as you get in simulation. I'm going to have to stop there. Gentlemen, that is as far as I can take you. That's what mountain guides sometimes say. You get to the top of the mountain and they say, gentlemen, that's as far as I can take you. Yeah, I'm a bit of an amateur mountaineer, as you can see from my wallpaper. That's not me, that's my daughter. I'm on the other end of the rope. I took that picture. Yes, we are climbing a mountain together. Question: is such a sensor useful for high current measurement? I have heard of fiber sensors for high current measurements. This is usually using polarization rotation. Those ones didn't use gratings. I've never seen a grating for high current measurement. I'm not saying it can't be done, but I've just never heard of that. I have a question about modeling of inclined fiber Bragg gratings. I presume that means the same thing as tilting. By tilting, we mean that the grating is not, the modulation of the grating is not perpendicular to the axis. It's not in the transverse plane, it's on another plane, which is inclined with respect to the transverse plane. Okay, there being no further questions, I'm going to say goodbye and thank you for listening to my presentation. I wish you all a good day, wherever